All right, get kind of hopping into things here. Hopefully, either Friday or today or sometime over the weekend, you had a chance to look at that additional recording. I think it was like 20 minutes. Just had some general probability stuff to kind of set us up, start talking about probabilities a little bit more practically. It'll make some of the stuff I talked about then will make a little more sense. On Wednesday, we'll hop into an Excel example of how we do what I talked about there and also everything we do today. In Excel, we'll see how we could take a data set and build those contingency tables, which I showed you in that video. I'll review a little bit about those as well as we jump into them and start talking about more rules here. But let's get into things. So we don't want to see that. That's what I want to see. So I actually reposted the week 3 lectures instead of kind of posting the lectures for this week. Since we were really finishing up last week's today, I just left those up there. I will post before Wednesday another set of lectures that will be for Wednesday, Friday, and then the additional video I do this weekend. So if we're looking at where I left off, I believe it was on this slide here where I said, you know, how do we read these contingency tables? So we've got kind of the column and row headings. So the top 4 left cells, we said all represented intersections. So this 0.4 was the probability that A and or A intersection B occurs. So I'm thinking about the probability of A and B, that probability would be 0.4. The probability of A complement and B complement would be 0.3. And then those totals, which we said we could get by adding across the rows, I kind of gave you a visual representation of why that works, or down the columns, these totals represent the probabilities of the events themselves. So the probability of just A is 0.6, probability of just B complement would be 0.5, okay? And remind me if I forget to kind of talk about this one here in a second. Once we get to one of our first rules, it'll be pretty clear why if we add these 2 totals, we should get 1, and if we add these 2 totals, we should get 1. So if we wanted the intersections, we could find them pretty easily. This is kind of a little bit of a review from that additional video I posted. And where I left off, and this becomes a little bit less clear, is how would I use, and actually, I want this to be open, not be so small as I'm talking through these. Hopefully that doesn't annoy too many of you. I think having the video of me talking hopefully makes it a little bit more personal, and that kind of actually helps as well. So if we want the union of A and B, right, we can think about what the union of A and B looks like. So first things first, I'll actually make this a little bit bigger, and instead of kind of flipping back and forth for a second, I'll just make this big down here. We can see everything that's in this table. So if I have, actually here, we'll do this and I'll go back to it. Let's say what I want is the union of A and B. So the first thing that I'm looking at is what's the union, and that was kind of that U sign, that set sign. And I've got this entire experimental outcome space, which I wasn't completely clear about this entire experimental outcome space represents every single possible outcome. So if we add up the probabilities of every possible outcome, just like when we were doing those histograms, if I add up the probability of every single bin, those should add up to 1. So this entire experimental outcome space, this square, rectangle, however it looks like I drew more of a rectangle here, represents kind of the area of 1, the probability of any outcome in this space, right? So let's say I've got event A right here, and I've also got event B. So the union of those 2 events, we said, was actually just what's in either one of these circles. So if I shaded in everything in this circle, that would be the A union B. But there's actually, I can break this down to 3 components, okay? So first, what if I took this kind of crescent moon area over here? Well, that's everything in A, but not in B. So it can't be in circle B, but it's in A. That's this little guy here. So this would be everything that's in A, and not in B. I do the same thing over here. I'll do this kind of crescent moon over here. That's everything that's in circle B, but not in circle A, right? So this is everything that's in circle B and not in A. Right? When I say not A, that's the same as A complement. That's what complement means, right? A complement means everything that's not in A. Well, the only thing we're left with here is what's in the middle. And if we do that, or let's see if I can draw an arrow down here. This would be everything that's in the overlap of A and B, right? Or the intersection of A and B. We looked at what that looks like with Venn diagrams on the extra video. So it's really, I can break down everything that's in these two circles into these three different components. So if these are the three different components I want, just as kind of a reminder, go back to the slides. I'm trying to find the union of A and B. So the three things I want are all right here. Right? So that's what I want to add these three components together. So the first one is the probability of A and B complement. So I'll go, okay, probability of A and B complement. That's 0.2. Add to that the probability of B or A and B. That's another piece that we need. So 0.2 plus probability of A and B is 0.4. And the final thing we need is the probability of B and A complement. So the probability of B and A complement is 0.1. So if we add these three pieces together, we should have everything that's in either of those circles, right? So I kind of broke that down into those three components, and now if I look at my contingency table, I get the union pretty easily, right? Now, I had to have a little bit of foresight to do that, and like, why did I break it down that way? You know, I mean, part of it's because I already knew it, but if we really just think about what we have in this table, we could have really thought about what each one of these meant. And so it's just a different way of kind of looking at what's in those two circles, breaking it down into those three components, so we could very easily, from our contingency table, find those three components, add them up, and we'll have our union. Right? Now, this is not a technical way to remember this, but another way to find the union, you can break it down always into those three components, right? And you'll always be able to find it. But let's say I wanted the probability of, let's say I wanted the, just want to get rid of this real quick. Let's say I wanted the A complement union B complement. So A complement or B complement. Now visually that'd be a little bit different on that Venn diagram. But what you can always do, this isn't like real technical, but I look at my contingency table. If I go to what I want the union of, so here I'm saying I want the union, and let's say I change this to A complement. So actually, let's say I change this to A complement and B complement. If I go to the intersection of those two things and make like a little L, if I add those up, that would give me the union. That's not a technical way to do it, but if I go to where the intersection is and make a little L, that would give me the union of those two events as well. So that's kind of a, I don't know, cheat code. It's not really like the most technical way to do it, but that'll always work as well. Now, that's the first way to think about the union. We'll talk about some probability laws today. And after we talk about one of them, we'll revisit the union, and I'll show you what I think is a much easier way to use the contingency table to find the union. Okay, but this is the first way. Right? Just one way of thinking about it. Okay, so this is still a little bit bigger than I want. So if we go down here, if I had like a sample question, right? And this is kind of a review of the extra slot or the extra video. What if I changed A and B to just R1, C1, R2, C2? It doesn't matter what those row and column headings are. Let's say I want the intersection of R1, C1. Well, what would that be here? Well, all I do is go R1, C1. The probability of the intersection of those is 0.4. These top four left cells always represent intersections. Okay, so if I wanted the intersection of R2 and C2, R2, C2. Also, I just realized I should definitely change this to D, so I could do like R2, D2. Does anyone, okay. Hopefully someone got a chuckle out of that. I'm definitely changing that, by the way. So We could find any intersection we want. That's not too tough, I don't think. The union here, when I talk about it, it's a little bit trickier, right? So we could break that down into 3 components. So we'll revisit this in just a second, but one thing I also want to talk about, anytime we're writing these very kind of first probability law we have, is order doesn't matter when it comes to the union and the intersection. Okay? So if I say that A and B happened, it's the same as B and A. Or if A or B, it's the same as B or A. Right? It doesn't matter which order in which I say them, it's the same thing, right? The best example is if I say, let's say event A is I'm over 30 and event B is I have brown hair, right? If I say I have brown hair and I'm over 30 is the same as saying I'm over 30 and have brown hair. The order doesn't matter, right? Or even if I change it to a union, if I'm over 30 or have brown hair, it's the same as do you have brown hair or are you over 30? Either one doesn't change what I'm looking for, right? So the ordering doesn't matter on the union and the intersection. And that'll help us out when we get to the multiplication rule later. Okay, so that's the first kind of, I guess, law we have. Now we think about kind of that intersection. This is always, I thought, was a fun meme, right? When you say it's fine, when it's actually fine, very small intersection, right? Probably that intersection is like 0.01. We can start to think about these using Venn diagrams. So the next rule that we'll use, and this is a really good visual representation of it, is the probability of an event and the probability of its complement have to add to 1. This is a good visual because if I take everything that's in A, that's the white shaded area, and then everything not in A, which would be this blue shaded area, or A complement, if I add those 2 areas together, I have this entire experimental outcome space, which should add to 1, right? I know the experimental outcome space is 1. I have a question here. So is A complement everything that is in B? No. So A complement literally means everything not in A. It could be in B. It could be in event C. It could be in event X. It could be in anywhere else. As long as it's not in A, it's in A complement. So if I go back, I think what you're asking, let me double check on something here. I am recording this. Okay, good. If I go back here, if I'm talking about A complement, well, this entire circle is A. It's just that part of that circle is A and B, right? Because there's an overlap there. But A complement would mean it's everything not in A. So it could be this area of B, but everything not in A also includes this area over here as well, right? So all A complement means is it's just not in that circle A, okay? It's a good question. So it's easier when I don't have event B on here to see why once I take what's in A and right, I could draw a circle here or something that hopefully looks somewhat like a circle and call this, circle B. That doesn't look like a B, but you get it. And yeah, A complement includes B, but it doesn't matter. It's not in A. Anything not in A, right? And so if I take an event and its complement and I add them together, it's this whole space. And the whole space, that area is 1, right? Because it represents the probability of every single possible outcome, which we know has to be 1. Right? Now, what I did here is I rearranged the equation a little bit. All I'm really saying here, kind of that general intuition that the probability of A and the probability of A complement here have to add to 1, that makes a lot of sense. So what we're really saying here is the probability of A plus the probability of A, ignore that cat, probability of A and the probability of A complement have to add up to 1. If I just rearrange things a little bit here, I might have to go throw them in the basement or something. Right? Then I get what you're saying on the slide, right? So it's just rearranging this general kind of intuition to get our complement rule, right? So the probability of any event's complement would just be 1 minus the probability of that event, right? And that's kind of how we get that from that other equation. We just rearranged it a little bit, okay? Any questions on that one? That one shouldn't be too bad. And this will pop up kind of behind the scenes in a lot of this different stuff we talk about in the next couple chapters, this complement rule. All right, so the next one we're going to talk about is the union. So this is where we're going to revisit the union. Give me 1 second. I'm just gonna load it in here. Hopefully it doesn't annoy us. So if I just want the probability of the union, right? Some people initially, you might think I can just take the probability of each event and add them together. And that'll give me the probability of seeing either one of them. Now, the problem with that logic is if I think about what I'm doing visually, I can say, okay, if I took the probability of event A, so this circle right here, and I added that to that, the probability of event B. Hold on. You gotta go somewhere else, but if you're gonna do that. Here he is. Okay. All right, hopefully we don't have to deal with them anymore. So if we take everything that's in event A, this circle, and we just added it to everything in event B, it's in this circle, what we've done is we've double counted what's in both of them, right? So if we've double counted something, yeah, we can just add them together, but we have to remember whatever we double counted, we have to subtract that out once, right? Can you refresh with the upside U? Okay, this upside down U, that means the intersection of two events, right? So the way we read this was, this is the, oh, I can get my mouse to show, here we go. A intersection B, or A and B, right? And this was A union B, or A or B, right? So because we double counted that intersection, we're gonna subtract it out once so that we're only counting it one time. And then that solves our problem. Now we can simply add the probability of two events up, subtract out their intersection because we would have been double counting it, and now we're just left with the union. If you want to think about the example I used in the extra video, I think I said event A was rolling a 2 or a 3 if I rolled a die. Event B was rolling a 3 or a 4. If I wanted the union, well, the union was just saying a 2, 3, or a 4. Well, if I had just simply added all the values in there, I would have had 2, 3, 3, 4. So I had to subtract one of those 3s out. That's kind of the idea. Those aren't probabilities, so it's like it's a little bit more of an abstract idea there, but it kind of gives you the intuition, right? I would have been double counting that thing that was in both of them. Okay? So once I know that I just have to subtract that intersection, right? Now I'm fine, right? And it makes my life pretty easy. I just add up the probability of the two events, subtract out the intersection, and that should give me the union. Okay. Any questions on that before I move forward here? I'm going to go back to, I'm actually going to move this one slide so I don't have to keep going all the way back up and all the way back down to show you this. If we go back to earlier, when we were talking about the union, okay. So if this is our law, we should just be able to take the probability of A plus the probability of B and subtract the intersection of those two events. If I look at a contingency table, where's the probability of A? The probability of A is just 0.6. The probability of B is just 0.5. So I'll add those together, right? Plug those in here. I could go 0.6, 0.5. Now I subtract out the intersection. So the intersection would be the probability of A and B is 0.4. So then I plug in my 0.4 up here. So 0.6, probably what I do. So I go 0.6 plus 0.5 minus 0.4 should leave me with what? I think it's 0.7. Also, I guess this should be down here. It's as easy as that, right? Once I have this equation, once I go back to that contingency table, it's pretty easy to find those three numbers. Instead of breaking it down into three components or finding the intersection, creating an L, it's not like the fail-safe way to do it. It's probably not the best way to think about it. I think once we know this rule, it's a lot easier to use this rule and then the contingency table to find that union. Right? Any questions on that? Does that make sense? wait for some questions here just in case. Okay. I won't waste any more time on that then. That's our union. So now that we know about this rule, one thing that can make that rule easier is if we have mutually exclusive events. So I think I've probably mentioned the term mutually exclusive before. It's probably to a detriment, a part of my language. But mutually exclusive just means that two things can't happen at the same time. So if I say that A is mutually exclusive from B, that means if something in event A happens, it can't be in event B. It can't have also happened in event B. So it would be like if I use my die example. Let's say event A was getting a 1 or a 2, and event B was rolling a 5 or a 6. There's no number I can now roll that would be in both event A and event B. So if I'm talking about the probability that I roll a number and it's in event A and in event B, well, that doesn't exist. It's not possible. So the probability would just be 0. The probability that I see something that's in both of these events, right, A and B, the probability, if it can't happen, the lowest probability I can have is 0. Right? There's just no chance it can happen. And so that simplifies our equation, right? Because now there's nothing we're going to double count. If I look at a visual of this, and I move my head, nope, move me over here. If I now look down here, right, now if I just add the probability of A to the probability of B, I've double counted nothing. So I don't have anything to kind of subtract out. Now I can keep the format the same, and really all I'm doing is then adding the probability of A to the probability of B and subtracting out the intersection, but the intersection, if they're mutually exclusive, is just 0. Subtracting a 0 isn't going to change anything, right? So, oops. That's kind of a nice little property of being mutually exclusive, is it simplifies the way in which we can find the union. Right? Also, if we know that two events are mutually exclusive, that their intersection, the probability has to be 0, that means if they're mutually exclusive and we have a contingency table showing the probability of the intersection of those two events, it should be 0. So if I give you a contingency table and I ask you if two events are mutually exclusive, the only way, if you don't see a 0 in that contingency table, there's no way they're mutually exclusive, right? The only way if you don't see a 0, I don't know if I said this correct, if you don't see a 0 in that contingency table, there's no way they could be mutually exclusive, right? The only way, in which they could be mutually exclusive is if the intersection is 0, which means you'd have to see a 0 in that contingency table. Okay. All right. So that's I don't think that's too tough. So we're then going to now use this definition of the union to think about something else we could think of. Take it a step further, I would say. So for right this second, I'll give you a visual to give you an idea of why it is the way it is. But for now, trust me, that this shaded blue area, right, is the intersection of the two events complements, right? If I'm looking at event A and B, everything that's not in either A and it's not in B, right? So it's not in A and it's not in B. Well, that is just the intersection of what's not in A complement, and what's not in B complement, right? So if I took that shaded blue area and I added to that the shaded white area, I filled up my entire experimental outcome space. So I know those two areas, that white and blue area, have to add to 1. So what is this shaded white area? Well, that is just everything that's in either A or B, or A union B. So I take the probability of A union B, add to it the probability of A complement intersection B complement, which I'm telling you that's what that blue area is. Trust me, for now that's what it is, and I'll show you why in a second. Those have to add up to 1. Well, I can substitute in, right? I have an equation somewhere. Here we go. I have an equation for what that union is. It's just the probability of the events added together, subtracting out the intersection, which we double counted. So I'll go ahead, I'll plug that in instead. And now I know the probability of A plus the probability of B minus their intersection plus this shaded blue area have to add up to 1, okay? And now if I have any 3 of these 4 pieces, I can solve for the one that I don't know. So maybe I know the probability of A, the probability of B, and the intersection, I can solve for the entire area of what's left. And this kind of makes sense. If something is in either A or B, well, that includes every possible outcome that's in either A or B. The probability that it's not within one of those circles would be whatever's left there. Let's see, chat real quick. I have a question. What about A and B intersections? Does the union take into account that? So the union is taking into account the intersection of A and B, right? Because the way we're writing out this union, it's taking the probability of A plus the probability of B, but when we do that, we double count the middle, so we subtract out that intersection. Now, if you're just simply asking, is the intersection a part of the union? Yes, it's one of the three, right? That was like when we broke this down into these two like crescent moons. So there's a crescent moon on either side, and then what's in both of them, that's the intersection. So when I say A union B, it could be in A and not in B. It could be in B and not in A, or it could be in both, right? It could be in the intersection. So the union inherently includes that intersection area. Hopefully that answered your question. Okay. So I want to give you a little bit, before we keep going, I want to give you a little bit better idea of why this is the intersection of the two complements. So let's go. Now, I hope these show up better than what they are to me. If not, and you have any questions, please let me know once I get down to the end. But I think that they should show up different enough. So let's say I have this experimental outcome space, right? And I've got event A here. Okay? Now I'm going to try to draw in blue lines where A complement would be. So A complement would be everything here. Right? And I'll put a bunch of lines just so we can really tell where it is. All right? Now, if I have event B, so all those lines, remember, if you want to like put down at the bottom, you know, something like this, blue lines, that's A complement. Okay? If I then have event B, B complement would be everything not in B, right? So just everything not in the circle. So these are B complement. Right? So now it might be a little hard to see, but like, right, even where there's blue lines here, there's no green lines. And even when there's green lines here, there's no blue lines. So the only place where A complement and B complement overlap, which overlapping is really just saying that it's in both A complement and B complement, or the intersection of A complement and B complement is really just this entire area outside the circles, right? Which is where it looked like when we look at this area, right? It's the area outside those circles. That's the intersection of A and B complement, right? So that's why that is what it is. Now, usually like in problem stuff, I'm going to be giving that to you. So let me see if I can give you a kind of a, there we go. So I'll hold this up kind of hopefully. There we go. So that's why that shaded blue area in the slides is the intersection of A complement, B complement. Now, in any problem, I'm going to like be telling you that's what it is, so you're not going to have to remember that. But I just want to give you a little bit of intuition behind the reasoning as to why. Okay. Any questions on that before we keep moving? We'll do a couple problems together. Okay. So let's look at a sample question here. So let's say I have all this information on the slide and I ask you, what's the probability of B? Okay. Well, I'm given the probability of A, I'm given the probability of A intersection B, I'm given the probability of A complement and B complement. So A complement, B complement is this like light blue shaded area. So I know what that is. And I know if I take that and I add to it the union of A and B, everything in the circles, those would add up to 1. But I don't have the union. The union wasn't told to me. But I was given the probability of A and the probability of, and the probability of A and B. So I can use those, and knowing that those two things would add to 1 to find out my missing component. Right? So if I go back here, we said this equation has to add up to 1. Okay? So if all I do is start plugging values in, right? So what was the probability of A? 0.5. So let me see if I can switch slides and write things in. I'm not sure it's going to let me do this, but find out. So I get the probability of A. It's not going to let me do that. It was 0.5. I didn't know what the probability of B was. If I go back to that slide, which I will here in just a second, it told me the probability of the intersection was, if you're looking at it on your own screen, 0.1. And it told me the intersection of the complements, I believe, is 0.3. If that's wrong, someone correct me. So now I've got everything plugged in. I know it equals 1. Now it's just a little bit of algebra, right? So if I plug all the things in that I know into this equation, now it's just a little bit of algebra. So I go back here, what I'm given, right? I could just write that equation down and do the algebra. So I'll do that for you here just to, in case anyone's kind of a little bit of help with that. All right, so we know that probability of A was 0.5. We don't know the probability of B. The probability of the intersection was 0.1, and the probability of the intersections of the complements was 0.3. So from there, it's, okay, 0.5 minus 0.1 plus 0.3 is just 0.7. So we'll subtract 0.7 from both sides. We're left with 0.3 on this side and the probability of B on the right side. So we've solved for the probability of B, right? It's really pretty easy. I mean, it's easy algebra where we have one equation, one unknown. Once we plug everything into our equation, it's just a matter of solving for that unknown. Okay? Any questions on that before I keep moving? You want to see something I wrote down again? I know I'm kind of switching back and forth quick. Hopefully you'll have the video afterwards if you want to go back, but feel free to stop me and ask me again. I can kind of show you it. All right. Can you show? Yeah, easy. Yep. Yeah, all right. So we just plug in those values. 0.5 was the probability of A. 0.1 was the probability of the intersection. And 0.3 was the probability of the intersection of the complements. And that probability of B is the one thing we didn't know. And I kind of did a little bit of the algebra in my head there. I added 0.5, 0.3, and subtracted. I knew that was 0.7, so I subtracted that 0.7 from both sides. Okay. All right, so you could be asked questions like that on the online quiz potentially. You know, you might see something like that on that first exam. I don't think that's anything too terribly tough. But if you have any questions on it, kind of let me know. I have another, and here's kind of some of the math that if you want to kind of go back. Another thing you could do if it makes more sense, I don't really think that it makes sense to do it this way, but you know, everyone's mind is different. You could first take the equation and just solve for what you don't know, right? So I don't know the probability of B. I could rearrange everything so that I have an equation that the probability of B here would be what? 1 minus the probability of A minus the probability of the intersection of the complements, and then plus the probability of intersections. Right? I could solve for the probability of B, since that's what I don't know, and then plug everything in, right? And that's kind of what I have here. Two different ways of doing the same thing. I personally think it's just easier to plug the numbers in and then do the algebra, but that's me. Personal preference, really, at that point. I've got another one here. Might just be some good practice. I'm not going to go through it now. It's got the exact same setup. It's just now you don't know what the probability of the intersection is. So it's really just this same equation. I'm just giving you 3 different pieces of information and leaving out a different one, right? And I could never only give you 2, right? It has to be that I give you 1 equation, 1 unknown. So I'd have to give you 3 of the 4 pieces of information. So this might be some good extra practice on your own before you do the online quiz, just to make sure you can reproduce the answer here. I've got it. Maybe I've got it. Oh, yep, there it is. I've got it there, so you can kind of try to work through it, check your answer. as you're kind of getting ready to take that that online quiz after class. Okay. All right, where are we at on time here? All right, any questions before we move on to this next topic? Okay. So the next thing we'll start talking about, and this is really, I didn't do any discussion. I kind of actually punted on some of the discussion of conditional probabilities in that additional video, but we'll start talking about them more now. I think I did the example of like, if I slip and fall outside, if the event B is that it's been raining, I know it changes that probability, right? So a conditional probability is the idea that if you give me additional information and you're telling me this has definitely occurred and it's definitely true, I now know the probability of whatever I'm interested in has now changed, right? So one thing that comes out of knowing something about the conditional probability is we have this multiplication rule. So multiplication rule is that if I want the intersection of two events, right, I can get that by taking the probability of the event itself and then multiplying it by the conditional, sorry, I'm going to say this again. If I want the intersection, the probability of the intersection of two events, so A and B, I can take the conditional probability of B. So the way we say this is, it's the conditional probability of B, because what's on the left side of this line, this conditional line, this is still what I'm looking for the probability of. So I'm still looking for the probability of B. I'm just looking for the conditional probability of B because I'm looking for the probability of B conditioned on A has already occurred, right? Given that A has occurred, what's the probability that B occurs, right? So this is still a probability of B, it's just now conditioned on A. So we call this the conditional probability of B, all right? Similarly, you can think about over here, this is the probability of A, it's just a conditional probability of A. I'm conditioning on that B has already occurred, but I'm still looking for the probability of A. Okay? So the multiplication rule says, for now, we'll just believe it. I'll try to give you an idea of why it holds. The intersection of two events is just the conditional probability of an event times whatever I'm conditioning on, okay? So let me see what I have in this next slide. So we can rearrange this a little bit. So this is like a multiplication rule, but to me, it's not as intuitive why this works. But if we rearrange things a little bit, so notice if I just divide the probability of A here on both sides, it would cancel here and now it would be over there. So that's all I'm going to do is rearrange those two multiplication rules. Now this gives me a little bit better of an idea about why this holds, okay? So I'm going to try to give you a pretty nice visual representation of why this will hold, all right? So let me just start off writing the rule down here real quick. So we'll go probability B equal to the intersection of B. Yeah, we'll use that first line, right? So I'm going to stop this share. Let me minimize this. So the reason why this works is, and I'm going to try to draw a really extreme example, so hopefully it sells it. So let's say I've got something like this. Right? So if I have, instead of circles, to make this make a little more sense, I'm going to, actually, I can do this a different one. I don't want to do this. I'll do it like this. So let's say over here I have event A, right? So the probability, if I just wanted the probability of A here, what should it be? If this is drawn somewhat to scale. No one even in the chat wants to help me out. If I split this in half, what should the, yeah, 0.5, right? So if I have the unconditional probability of A, the probability should be 0.5. But what happens, right? Let's say I have I have area over here, and this whole rectangle down here is event B, okay? So the probability of B, I'm trying to draw it, would also be 0.5, okay? and then I had this, right, was event A. Well, now if I think about what's the probability that B has occurred, if I know that A has already, I know for sure that A has occurred, now what's the probability that I'm also in B, right, or that B has occurred? Well, if I know that A has occurred, I'm limited down into this space. And of this space, how much of it is B? Right? This right here, well, so this would represent the probability of A and B. And now that I know I'm limited down to just the space of A, I no longer am working off of that entire experimental outcome space of 1. I'm only working off the space of whatever the probability of A is. So 0.5 here, the intersection with then 0.25. And now the conditional probability of B, unlike the unconditional probability, is going to be, actually here it doesn't change at all, right? Because these were, because the way I drew this, I equally split. So it could be that the conditional and the unconditional probability are exactly the same, right? It could be. The way I drew it here, we actually end up with a situation like that. But you can kind of imagine, like, it's no longer like, what is the area of B out of the entire experimental outcome space? That's how we got probability of B. Now it's like, once I condition on A, I've cut my experimental outcome space down just to wherever A is. And now what's the probability I see B? Well, it's just the fraction of whatever the intersection is relative to that event. So it's the fraction of whatever the intersection is relative to that event I've conditioned on. Right? So that's why that multiplication rule works out. It's kind of easy to see it there when you just split it equally with rectangles, I think. I could give you another example. So let me erase this. Actually, before I say it, did anyone want me to did anyone want to see that again before I erase that? We're okay with this? All right. So I'll give you a little bit better idea about how the conditioning could change. So let's say instead, I have something like this. Go real extreme here. So entire experimental outcome space. Here's, let's say this is event A. Well, no. I'll make it even more ridiculous. I'll go the opposite way, I'll go small. So let's say this is the event A, right? Probability is pretty small there. I don't know what it is. I don't even have to put a number to it, but you can see it'd be very, very small, right? Maybe like 0.05, would just be generous. So let's just even assume the probability just of A occurring is 0.05. And then I say, okay, but what's the probability of A given that I know B has also occurred? Well, what if event B was like this? Something like that, where it almost exactly mimics A. Well, now that I'm limited to the space of B, most of that space of B is also A. So now the conditional probability of A, once I know I'm somewhere in circle B, well, now this is probably almost 1, right? These circles almost exactly overlap, okay? And so if you have like really, really, overlapping events that have a really high intersection, well, it makes sense that if you tell me that one of the events has occurred, then the probability the other one occurs is also went way, way up because they have such a high intersection. All right, where are we at in time here? Any questions on that? I'll leave this open here. Okay. But, regardless of where they come from, these are going to be the kind of the rules that we can use. The conditional probability will really just be the fraction of the intersection of the two events that you have, right? The probability of the event you're looking for and whatever you're conditioning on, the intersection of those two events divided by, or the ratio of that to whatever the event you're conditioning on is. Because if you think about it, when you condition on an event, you've now limited like that denominator. You've decreased it from 1 down to whatever the size of that event you're conditioning on is. All right. So this is just kind of a reminder slide of all those different rules. which is kind of a nice place where you can look back as a reference. You've got your addition rule. You've got, and you can think about, I put down here, if I rearrange this to solve for things, I could think about different variations of it. Multiplication rule, could be written either way. This is the one I think that's a little bit more intuitive. But if we rearrange it, let's say I gave you a conditional probability, you could find the conditional, or you could find the probability of the intersection. Now, one thing about this conditional probability, if I don't know what they are, one nice thing, if you look at this, if I have a contingency table, pretty easy to find the probability of A or B, also very easy to find the probability of the intersections of A and B. So I can use a contingency table now to find my conditional probabilities, even if I don't know what they are, or I'm like not directly given them. So I showed you an example of this already. So I'm going to, well, I erased it now, so that sucks. I'll draw it again here in a second probably. But we say two events are independent if the conditional probability of the event, so right, I'm still looking for the probability of A, I've just conditioned on B occurring. If that conditional probability is equal to the unconditional probability of A, we say those are independent events, right? It doesn't matter if I know that B has occurred, the probability of A hasn't changed at all. So if we go back to that one where I like split it in half, the probability of A ahead of time was 0.5, right? Once I conditioned on B, well, even though I limited the experimental outcome space down to 0.5, still of the space left, half of it was still B, and so the probability of B conditioned on A was still 1/2, right, 0.5. So that was an example where it didn't matter if I knew that B had occurred, the events were independent, right? That'd be, it's not the same as mutually exclusive, right? Those two events were definitely not mutually exclusive that I drew. They had a very large overlap. There's a very large intersection there. It was definitely not zero. It's just that, for whatever reason, of the entire experimental outcome space, the ratio of the entire experimental outcome space, well, here, I can think of a good one, I think. Try to think of something that's like equal across Republicans and Democrats. So maybe like one characteristic that wouldn't be, oh, I got a good one. Actually, I'll change it. So for the sake of this example, think of if we had kind of a gender binary where we were able to break down kind of men and women, right? It's about 50-50 in any country. Some countries are a little off, but it's about 50% male, 50% female. If we said, okay, what's the probability of the males? What's the probability they have brown hair? Or sorry, what's the probability in general that someone has brown hair? Probability of event A is that you have brown hair. I don't know. Let's say it's 0.6 or something. I don't know. So you say it's 0.6. Well, then you say, okay, conditioned on that the person is a male, what's the probability they have brown hair? Well, the ratio of men to women with brown hair, if we're talking about natural hair color, is going to be pretty much the same, right? That conditional probability is, having that additional piece of information isn't going to impact the probability of what we're looking for. So they're not mutually exclusive by any means, right? Plenty of men that have brown hair, but they could be independent. So if we return to kind of our multiplication equation, that simplifies things for us, because now if I look at the conditional probability, well, if I know the conditional probability, if they are independent events, then the conditional probability should just be the unconditional. I could actually just plug in, oops, I'll have to reduce the chat here, the probability of B here. And so now my multiplication rule to find what the intersection is just becomes take the probability of those two events and multiply them by each other. So we're kind of running out of time here. I want to go through a few more things. I'll show you, we'll pick up with independence again on Wednesday. I'll use the contingency table to show you some more things about independence. We'll talk about checking for independence, and then we'll kind of jump into an Excel example. So we'll do a quick refresh on that independence idea and the multiplication rule on Wednesday. We'll then jump into this union membership data set that I'll have up on Canvas. I believe it's already up there. And we'll start constructing our own contingency table. So all these, I gave you the numbers, right? How could I actually build my own contingency table from an Excel data set? And then I'll go through some, I think, fun problems, hopefully Wednesday as well. We'll have a little bit of time to kind of go through those, okay? I know, let me just say, I'll pull the chat open just in case there's any questions that we can in class. I'm behind on grading because of last week, so I'm hoping tomorrow to get all your individual assignments graded and start working my way through your Excel documents. So please, hopefully, you'll have a little bit of grace with me because of getting sick. That I'll get caught up here in the next day or two on all that grading, so that you guys will start to get an idea about how you did in those assignments and kind of move forward. So after Wednesday's class, I'll probably post the next Excel assignment. We won't have done everything Wednesday, but at least a portion of that Excel assignment you can start to work through with a data set. And actually, I'm going to look at it. It'll either be an individual assignment or an Excel assignment. Probably an Excel assignment, but it just depends. I'll look at kind of what we've done, examples I have, and think about which one would be more accurate. This assignment to be individual or Excel, or the next one I have planned. So other than that, are there any questions for me? I whole 100% plan on being in class, having in-person classes Wednesday and Friday, which this week, let's just keep it consistent with what it was showing. So we'll do group 2 would show up Wednesday, group 1 would show up on Friday, and then next week we'll go back to what it should have been the week we missed, which is group 1 comes back on Monday and Friday, group 2 shows up Wednesday. So we just kind of keep it consistent this week and next week. So group 2, you would show up on Wednesday, group 1 on Friday this week. Any questions for me? Here, I got one, except for I can't see it. What makes them independent if they are overlapping? So if you want to leave now, you can, since class is over, but I'll answer the question. They're independent if they're overlapping. All independence means is that they don't influence the probability that they happen, right? So it's the idea that just because I have this piece of additional information, it doesn't change the probability. So it's like these two things are independent from each other, right? Being male or female, and actually I shouldn't speak like I'm a biologist, I'm pretty sure this is true. Being male or female does not have any influence on your hair color, right? Or being male or female doesn't have any influence on my eye color. So if you tell me that, it just doesn't matter. Or if you tell me your age, right? Well, age, I guess it would influence hair color. If I told you someone's age, you probably wouldn't be able to have, it wouldn't change the probability that they have blue eyes or brown eyes, right? That's remained fairly consistent. Let me think of another one I could use. Independent events. So if you tell me that it's sunny outside, as long as cloud coverage in an area is pretty similar throughout the year, just because it's sunny outside doesn't tell me anything about whether or not it's windy. I guess maybe storms, I don't know, that's a bad example. Trying to think of something else where like it's basically you're given a piece of additional information that just doesn't, there's no systematic differences across whatever you condition it on. So that's why I thought, to me, like the gender eye color one makes sense, right? Because as far as I know, eye color isn't related to gender. If there's any biologists in the room that, or biology, like double majors that know that that's not true, let me know. But as far as I know, that's the case. Does that make a little more sense? Yeah, okay. All right, any other questions, comments, concerns? Hopefully everybody's doing well. I'll see group 2 on Wednesday and group 1 on Friday. I'll also post an online quiz today that I want you to get done before class on Friday. Or sorry, Friday. Class on Wednesday. Okay. We'll see you guys later.